Welcome everyone to the first and kickoff presentation of this season. It's a great pleasure for me to introduce the speaker, Professor Vineet Goyal. So Vineet is a professor in the Industrial Engineering and Operation Research Department at Columbia University, where he joined in 2010 as uh, where he joined in 2010 after a PhD from Carnegie Mellon University, graduated in 2008, and a postdoc at MIT. So his postdoc was actually with Dimitris Bertimos, and nice and the fundamental theoretical results came out of that. He's interested in design of efficient and robust data-driven algorithms for larger scale problems on the dynamic side of the applications and dynamic optimization with specific application focus in revenue management, healthcare, and resource allocation. And of course, his research has been also supported with many grants, including the ones from NSF, DARPA, and the industrial, including the NSF Carrier Award. So it's a pleasure to have you here, Vineet. And without further ado, I want to give the control of the mic and screen to you.
Thank you, Reza. Thank you for the invitation to Yanis as well. It's a pleasure to be doing the first talk of the spring, and thank you all for being here. I know for some of you, many of you, it might be late Friday afternoon, time for the weekend. But so thank you for being here. So this is joint work with my former student Ayub Fosul, who is a postdoc at Booth U Chicago right now. Uh, when I'm saying joint work, I'm lying a bit. It is really his work, and I learned a great deal from him, and hope to present it here. So this work is actually it considers a very classical problem, the news vendor problem, the first problem OM and OR literature would have looked at, and a very fundamental generalization or variant of that problem. So let me jump into the motivation for this work. The news vendor problem, the classical news vendor problem is models the following trade-off. A seller is facing an uncertain demand and needs to decide on how many units to buy. And the fundamental trade-off is you buy one unit more than is needed. You pay a holding cost for an extra unit, or if you buy a unit less than the demand, then you incur some back order penalty for the lost demand or the opportunity cost. So the news vendor quantity or the optimal quantity for the classical problem balances these two trade-offs and gives us a closed form solution in actually many settings. If we know the demand distribution, we have a closed form solution also for some variants of unknown demand distribution. In this work, what we were focusing on was a very fundamental generalization. So still with a single product setting, but now you are planning for inventory at multiple warehouses that are distributed across the metric. Uh, this arises in almost any e-commerce companies where the warehouses are distributed in space, and you need to plan inventory for all the warehouses before you see the demand. And in fact, once you plan the inventory, the demand doesn't appear all at once. It appears sequentially. It appears one by one, and when the demand appears, you need to make the allocation decision of which warehouse to go to. Okay, so this is, I think, a very fundamental generalization of the news vendor problem, and it arises in almost any e-commerce application where you want to distribute inventory across place. You could have planned each warehouse no, typically serves a region, right? One could actually solve independent news vendor problem across for each of the warehouses for the demand that warehouse is serving. But then that would be highly suboptimal because one could be losing, one could be leaving significant money on the table uh, by not risk pooling across regions. There is always a recourse decision of shipping inventory from some other warehouse than the closest one. Okay, so and we one in especially in e-commerce application, one has the option of a flexible demand fulfillment in when you see the demand. Okay, so the question that we want to look at in this work is how to jointly plan the inventory across different warehouses distributed in space, and then once I have the inventory, how should I fulfill the demand that arises sequentially over time? Meaning, when I see the demand, uh, I need to make a irrevocable allocation or assignment to serve that demand from a unit in one of the warehouses. Okay, so these are the questions that I want to look at in this talk. Now, I think many of you might be wondering, this is a age-old problem. Why? What is the new take here? And I had the same view, but I had the same view about this problem that this is a reasonably studied problem in some settings and solved problem. And one example I can give you is let's think that we know the demand distribution across different warehouse regions. Uh, I could sample the scenarios I could sample demand scenarios and just optimized over a empirical expected objective using sample average approximation. And that's a perfectly valid approach. There are some limitations. Yeah, we don't know the demand distributions. The demand distributions are known up to certain errors. So one has to be careful in modeling that. But one thing that was very surprising to me, and I work closely with Amazon. So whenever this problem is something that they're solving almost every week, uh, and using heuristics, this whenever discussion of this problem arose, I was it was surprising to me that okay, why would we not use a sample average approximation approach? And that is when it occurred to me that yes, sample average approximation does solve the problem, but uh, it's a black box in the sense that it does not give me an interpretable solution, in the sense that I cannot explain why inventory of certain warehouse is higher than the inventory it would have carried if I was solving an independent news vendor problem versus solving that big SAA problem. So interpretability of the solution is lost in that black box approach, among other limitations that we are optimizing too much to the assumed distribution where we sample the scenarios from. So finding a solution, an inventory solution, and a fulfillment policy that has a nice, explainable, interpretable structure, but at the same time is robust, was the main motivation of this work. Uh, so uh, okay. So let me just start with the model. Just to, and I'll use this example to explain the model. So the first decision of the model, the first decision in our model is the inventory decisions at each of the warehouses. So on the slide here, let's say I make the following inventory decisions. Number of units is the number of boxes at each of the warehouse, and then you see then the demand is sampled from some distribution, and I'll get to that. And then you observe that demand one by one. Okay. For instance, the first demand is in the bottom left, and then we make the allocation decision that is irrevocable for this demand. Okay. The second demand in the on the on the top left, we make the allocation decision, and so on. Okay. So this is the setup, and we pay a holding cost on the leftover inventory and a backlog cost on the unfulfilled demand. That's the usual news vendor problem. But in addition, we pay the shipping cost if you for all the units shipped across the network. Okay. Okay. So our cost for inventory vector Q, a fulfillment policy pi, which decides the allocation, and a demand scenario D is the following. So the first term here is the shipping cost. Okay, let's say it cost Lij to ship from I to J, and Xij is the number of units shipped from I to J. So that's the shipping cost that is decided by our fulfillment policy. We will assume that the shipping costs satisfy the triangle inequality, which is a reasonable assumption, which is actually without, I would say, without loss of generality in most practical settings. And then for the leftover inventory at the end, we pay a per unit holding cost of H, and uh, overall unmet demand, we pay a per unit back order or backlogging cost of B. Uh, I want to pause here and just mention a few assumptions that we make in our model. We assume that the holding cost and the backlog cost are the same everywhere in the network. Now, the backlog cost being the same across the network, that is reasonable because we are talking about a single product. The backorder penalty is more a product dependent quantity. So assuming B is the same throughout the network for this product is reasonable. uh, the holding cost being the same across the network, that is a limitation because we know that the warehouse costs or the capacity costs are different in general, different at different places in the network. So that is an assumption right now we have in our results, required for our results, and relaxing that would be an interesting open question. Uh, and then the first term is the shipping cost. Okay. Now one more element before we have all the elements of the model is how do we model demand? Um, uh, Now, the classical setting is you model demand as a stochastic using a distribution, and you want to minimize the expected cost. Okay, and this is where the SAA approach also comes in. What I was describing, if you know the distribution, you can sample demand scenarios, sufficiently large number of demand scenarios, and solve a two-stage LP. Okay, which the size of the LP will depend on the number of scenarios. So you can solve that. It has a limitation. The first limitation I mentioned, that the solution is more like a black box. I cannot explain the structure of the solution. But moreover, it also may be overly optimizing, assuming the known distribution, and therefore may be highly sensitive. The solution may end up to be may end up being highly sensitive to even small changes in the distribution. So to uh, address that limitation, there have been approaches suggested, including the approach of distributional robust optimization, where we don't assume a distribution to be known, but rather we assume that the distribution belongs to some distributional ambiguity set. And in this work, we will consider a moment ambiguity set that have been very widely studied in the literature. Okay. And by the way, I'm just putting a small set of references. If I for distributional robustness, I know many of you have worked in this area deeply. If I were to review I can spend the whole hour just reviewing the literature on that. Uh, uh, in addition to moment ambiguity sets, there have been other distributional ambiguity sets that have been looked at, including the phi divergence or Wasserstein metric, etc. But that's not the focus of this work. So in this work, what we look at is what we consider is a moment ambiguity set, which is basically given by known moments of the distribution. So what we assume here specifically is the following uncertainty set. Suppose I know the mean and the variance of the demand at each location. Okay? Uh, and we look at the set of distributions that satisfy the given mean and the variance. Okay? And our distributional robust problem would be we want to find an inventory solution and a fulfillment policy that minimizes the worst case expected cost, news vendor plus shipping cost, over the set of, where the expectation is taken, the worst case is taken over all set of distributions with these given moments, mean and variance. Here I want to emphasize this is another limitation or assumption in our model that sigma is diagonal. So it's uncorrelated. So demand is uncorrelated across locations. And just for the purposes of this talk, we will assume that demand is at the same location as the warehouses. So if the demand arises at the same way at the warehouse, you assign a unit there. Otherwise, you assign that demand to some other unit in the network that is decided by pi. Okay. So I can pause here to see if there are any questions. By the way, I should have mentioned earlier, the goal in this talk is to convey only a few set of ideas. So please feel free to interrupt if there are any questions.
I
I
have a
have a
short.
question.
Yeah.
Okay, go ahead,
No,
sorry.
go ahead.
I want to know whether there are also constraints or is it unconstrained?
A good question. So there are no constraints here.
Okay,
There are no capacity constraints here. That would
okay.
be an interesting variant as well.
Yeah, I also
You
have a very short. Sorry.
just to clarify that, Reza, did you mean constraints on upper bound on of inventory on at different warehouses?
For example, yeah.
Yeah. So there are no such constraints. So it's a
Okay.
completely unconstrained
Yeah,
Q is non-negative. That's the only
yeah.
constraint.
Yeah, my question was, is there a time component on the mean and the variance? So I can imagine over time, like especially when it's about demand, you have different demand in a
Yeah. Yeah.
different time
Thanks.
period.
Yeah, thanks, Yanis. I think, yeah, I should have clarified this. Yeah, thanks for this question. So this is really a two-stage, you can think, even though the demand we see sequentially, but in spirit, this is a two-stage problem where in the first stage, we plan for the inventory. And then the adversary looks at our inventory, picks a demand distribution from this ambiguity set with given mean. This is a constant mean vector, and then samples the demand from that distribution. So there is no time component in the demand, but adversary can reveal the demand in any sequential manner it prefers. So we don't impose that it is IID sample from the distribution picked. So it samples all at once and then reveals it to us in any arbitrary order.
Okay. Yeah.
Okay. Uh, any other questions? So if not, let me proceed. The way this is again not a new setting. In fact, this has been looked at in for the news vendor problem for a single location, and there is a famous paper of Scarf in 50s, and this is really the first reference on distributional robust optimization that I am aware of. If someone knows an earlier paper, please do let me know. So this Scarf considered this classical news vendor problem under this distributionally robust setting when there is a single location, single product, single locations. So you're facing the same problem as the news vendor, decide inventory, where you want to serve demand with mean mu and standard deviation sigma. And the paper derived the following closed form optimal. Okay. And the closed form optimal has a very nice interpretable structure. It is mean plus standard deviation times some factor, half of square root b by h minus square root h by b, which is a very nice and interpretable solution. It is in some ways, in fact, I find this even more interpretable than the classical news vendor problem, which takes the CDF inverse of a fractile. Okay. And the factor in front of the standard deviation also has an economic interpretation. So I find this to be a beautiful result. If you have not seen it, it's a short exercise of using Cauchy-Schwarz. So I would encourage you to derive this yourself. But nothing was known for the multi-location setting. No, this being a fundamental variant of the single location setting, but no structural results with any guarantees were known. But that said, there has been literature looking at the multi-location setting, but more from a heuristic point of view. In fact, the closest to our work would be a paper by Govindarajan et al., who looked at the case of two locations in a lot of detail, but still were able to only derive some heuristics to find the inventory solution. And the goal here was to actually get a solution, inventory solution, and a fulfillment policy that has this nice structure that Scarf has, or something similar, but still has some theoretical performance guarantees. Okay. Um, okay. So let me what can we say? So we can derive a near optimal policy, both inventory solution and a fulfillment policy that has a nice structure, simple and interpretable, almost as simple as Scarf. Of course, we can't achieve exactly Scarf, but almost as simple and interpretable as Scarf, with performance guarantees. So we lose optimality, but we preserve the simplicity of the solution given by Scarf. uh, with some provable loss in optimality. Okay. And also the fulfillment policy is can be very easily stated. So it's almost greedy. We call it the hierarchical greedy. So it also falls out very it is also a simple and interpretable policy and falls out nicely from our solution approach. We give provable performance bounds on our policy, and in particular, our policy achieves a polylogarithmic approximation, polylogarithmic in the number of warehouses. Now, from a practical point of view, polylogarithmic may not fly well with the practitioners, but the optimizing the bound was not the focus of this work, but rather getting a solution with some explainable structure, but at the same time with some performance guarantees, was the main focus of this work. That said, we also have some understanding of why the even the simple problem cannot be better than log. So there is some inherent hardness sitting inside this multi-location problem, especially in a sequential setting. Okay, and we do test the empirical performance of our policy, which turns out to be significantly better than the worst case theoretical guarantees. So worst case theoretical guarantees, as is the case in many problems, they so one, you're taking over worst case, therefore we are hitting some hardness lower bound that the guarantee cannot be better than that. But also there is some limitation in the analysis that makes the performance upper bound that we provide to be a bit looser than it might be even in the worst case. And empirical performances doesn't suffer from those drawbacks, and usually turns out to be better than the theoretical guarantees. Okay. So let me start with a short warm up. That tells us that demonstrates one key idea in this in our solution approach. So the simplest setting that is beyond the single location setting is a uniform metric, meaning all warehouses are equidistant from each other at a distance of L from each other. So here, I think the picture is a bit misleading. Here, every two warehouses are distance L apart, not unlike the star that the picture says. Now, in this case, uh, what we know is, and just to recall, we assume that demand locations and the warehouse locations are the same. So demand arises at the warehouse itself. So if a unit of demand shows up at some warehouse and you are out of stock at that warehouse, we know the unit you will fulfill that demand. How much is the shipping cost you have to pay? L. If there is any unit in the network, right, you pay a shipping cost of L. This assumption of uniform metric simplifies that, because wherever you go, you're paying a distance of your shipping cost of L, right? It doesn't matter where you are going. You know how much cost you want to pay. Okay, and that simplifies some intuition of the inventory policy. Now, if I think from a perspective of a single warehouse, uh, I can uh, uh, I can put a virtual backorder penalty on that warehouse. So in particular, I would say that the virtual backlog, the in the original problem, if I was out of stock for a unit, I was paying B per unit, right? For for every unit of unsatisfied demand. Now, in this network, if I think from a perspective of a single warehouse, the cost I'm paying if I'm out of stock is not B, it is just L, right? Because I can assuming there is a unit in the network, I can pay a cost of L and satisfy that demand. So if I am thinking from the perspective of just a single warehouse, I should think of the effective backlog penalty to be, or backorder penalty to be, L. And in fact, not just L, because I will ship that unit from some other warehouse, that unit is not going to pay a holding cost in that other warehouse. So it should be L minus H. Okay. Uh, so, so that is the virtual backlog or effective backlog that I would consider for this location. Okay. Now, that has this backlog cost assumes that there is unit in we are carrying overall, we are carrying enough inventory. Okay, and that is but so if I just look from a single warehouse setting with this virtual backlog, Scarf would say I should carry um, these many units at warehouse I. Okay. So this, if I think this is the virtual backlog cost, L minus H, if I look at warehouse I, this should be our inventory at warehouse I. Okay. Now, this virtual backlog cost is supported only if I have enough total units in the system. Okay. And that would mean that the total units should be the scarf inventory, assuming all the warehouse is a single location, right? Now I gave you a set of equations. These equations may not have a solution, by the way, right? I gave you as equalities. Each warehouse has an inventory, has QI, which is a equality, and then summation of QI is some other equality. This may not be, these set of equations may not be feasible, right? So what we do is we say, okay, let's think of them not as equalities, but as lower bounds. And we minimize the total units such that at each warehouse, I carry at least the scarf inventory given by the scarf formula, assuming a backlog of warehouse I as L minus H. And the total inventory in the network should be at least the inventory given by the scarf formula, assuming the full network is a single location. Okay. And the key idea in this in this approach is that if I am out of stock at a warehouse, I don't charge myself the full backorder penalty B, which is what an independent news vendor would have done, right? I just charge myself L because okay, I would pay L to get a unit from somewhere else in the network. And then overall, I should carry enough inventory, and I let the LP decide how these units are distributed across the network. There may be multiple optimal solutions, but yeah, which constraints are tight will be decided by the LP. Okay. What we can show is that okay, before I go to the fulfillment, what we can show is that this inventory policy gives a constant factor approximation for the problem, for the batch fulfillment problem, where we see the full demand at once. So if I look at the setting that you plan for the inventory, adversary looks at your inventory solution, picks a distribution, and picks a distribution from that moment ambiguity set and gives you a sample of demand from that distribution all at once. Then we can show that for the uniform metric, this LP, the inventory solution that we will get from this LP, gives us a constant factor approximation. Okay. Now, for the problem that we initially started with, sequentially arriving demand, the fulfillment policy we use is a very simple policy. If demand arises at a warehouse where we have inventory, we fulfill it from that warehouse itself. If not, then go to a random warehouse that has inventory. Okay. And for those of you who might have seen the caching problem, uh, the policy is very similar to that, but also there is a hardness of log of number of locations sitting in that caching problem, and the same hardness we sort of inherit, although there's no approximation preserving the reduction between the problems. But this gives an intuition that we may not be able to beat a factor of log in the sequentially arriving demand case. And we can show that this inventory policy and this fulfillment policy for the sequentially arriving demand gives us a log in approximation. Okay, for the simple case of uniform metric. Okay. Any questions? Okay, so now how do we extend this to a general metric? Now, in the uniform metric, the idea that if you are out of stock, you will pay L. Because it was uniform, I knew exactly what I was going to pay. But in a general metric where distances are arbitrary, when I am out of stock, so I want to define the same, I want to use the same idea of want to define a virtual backlog cost for each warehouse and just write the same LP. But now, when I'm out of stock for a demand at a warehouse, I actually don't know how far that unit will have to, that demand will have to be fulfilled from, because it's a general metric. Uh, so so to address that issue, what we do is we cluster, we compute a special hierarchical clustering of the locations. Think of this as putting those locations in a tree type of metric where closer locations are in the same cluster and so on. Okay. And so let me explain it by picture. So suppose this is a region, we create a tree-like clustering. So we first divide this full region into two children. Then each of these child is divided into further subregions. So the left child here is divided into four subregions. The right is divided into three. And so on, and the regions are further split. So think of these hierarchical clustering as putting a tree on the given locations, or creating a nested clustering of those locations. Okay, what this allows us is trying to define a virtual backlog of the virtual backlog quantity that was needed for that LP. But now in order to do that, we don't just define a virtual backlog of each warehouse, but we will need to define a virtual backlog of at each level in this hierarchical clustering, at each level of this hierarchy. So in the tree metric, for each subtree, one needs to define a virtual backlog cost. Okay, and to define that backlog cost, one can think of the following fulfillment policy, because that will actually depend on the fulfillment policy. In the uniform metric case, it didn't matter what the fulfillment policy is, which warehouse you are going to if you are out of stock, because everything was you were paying a cost of L. Here, the fulfillment policy decides how much shipping cost you pay. And therefore, the fulfillment policy is very closely interlinked into how I define this virtual backlog cost. Uh, okay. If I think of the fulfillment policy in the following way, so think of this metric, this various locations being put in a tree where all the warehouses are the leaves of the tree, and then the sub trees are just clusters. Okay. Uh, the fulfillment policy, let me state simply, is you try to fulfill from your warehouse. Otherwise, you go to your parent, the subtree of your parent. If that is doesn't have a unit, you go to the subtree of your grandparent, and so on. Okay. And that's the idea of the fulfillment policy. And based on that fulfillment policy, we can define this surrogate function, a surrogate that we will optimize instead of optimizing the original cost, which had the shipping cost plus the holding and the backlog cost. By the way, holding and backlog cost are easy because holding is paid on H per unit of leftover inventory in the whole network. And this is where the assumption of H being uniform across the network helps us. And similarly, backlog of any unmet demand in the network. So those components are fine. It was the shipping cost that was that was complex because that depends on the sequence of demand arrival and your fulfillment policy and so on. So we want to create a easier surrogate of for that shipping cost, and the surrogate is the following. So the first two components are just the Newsvendor components that I said we borrow from exactly from C. Okay, there's no approximation in the first two components. Is the shipping cost that we approximate it as. The shipping cost that we approximate is the following. We say that if you are not able to satisfy the demand, you go to the subtree of your parent, and then if you go to the subtree of the parent, even then it's unclear what how far you have to go. But then we charge ourselves the diameter of the subtree of the parent. Okay, we charge ourselves the worst possible cost. And this is where some properties of the clustering are helpful, where distances, as we go higher in level, are increasing by some factor. So even if we are charging ourselves the full diameter, it's not too much more than the smallest distance in that subtree between two siblings. Okay, and we sum up over all the clusters. Okay, meaning all the subtrees. So this surrogate allows us to makes our life much simpler and is amenable to much easier optimization than the original problem where these xij's, which was these assignment variables that was coming out of solving a matching problem, okay, where we don't have a handle on. Okay, what we can show is that this surrogate is both upper and lower bounded by some factors of the original cost function, and therefore we can optimize over that surrogate. But to show that, we have to fix a fulfillment policy. So this surrogate is not true for any fulfillment policy. It's true for the fulfillment policy that I'm going to describe, that I just said in words. You'd satisfy from the closest subtree that has going higher up in levels to the closest ancestor that still has a unit, and you satisfy from that. So let me explain it from this picture. Here, suppose the inventory position is given in the map on the right, the rightmost, the fourth map. The shaded region, the gray and white shading, those regions don't have inventory. The solid gray have inventory. Okay, and suppose demand arises in a warehouse or in a region where there's no inventory. Okay. So what you would do is you would go to your parent. In this case, the parent is this is the parent, right? Within this parent, you have two children. Okay. Or actually, this parent had three children. One of them did not have inventory. So you would try to satisfy uh, your demand with probability half from one child. So two of the children had inventory. So you would split equally. So with probability half, I'll go to region one, and probability half I'll go to child two. Okay. Now within each of those two regions, there are sub-regions, and I would split the probability equally there. So so 1/3 times 1/2, you would go to each of these regions. And similarly, in the other case, you had two children who had inventory, you would go there with 1/4, 1/4. Okay. So it's uniform greedy. The fulfillment policy is a randomized fulfillment policy, which is uniform greedy in respecting that hierarchical clustering. So go to the subtree, go to your ancestor who still has a unit, the lowest ancestor who still has a unit, and then just go randomly based on that hierarchical clustering as demonstrated by this. For this fulfillment policy, we can show that that for any inventory vector and demand realization and any sequence of observing the demand, the original cost is upper bounded by log square n of the surrogate. So surrogate is not too far. Okay, so you have an upper bound, which means you have an upper bound also on the expectation. Okay, you have an upper bound also on the expectation with any distribution, and therefore also the worst case expectation. Okay, now in addition, we also have a lower bound. So we can also show that the surrogate, uh, the worst case expected cost is lower bounded by the term in the surrogate, which was related to the diameter of the parents times the excess demand within each subtree. Okay, and that gives us a lower bound on the original cost is lower bounded by the surrogate, and therefore we can optimize the surrogate instead of the original cost function to get a good solution. What I have these parameters alpha, beta, gamma, and k. These are parameters of the clustering, and we can show that there exist clusterings where all those parameters are log. So you will get a log to the 4, and therefore you get a log to the 6 factor between surrogate and cost. Okay. Okay. So the parameters are, so let me define. So diameter of the cluster, we know. Margin is how far is your the minimum distance between siblings in the same level. Alpha is diameter by margin. Beta is number of families. K is number of levels. And gamma is the margin between two levels, the ratio of margin between two levels. So we can find a clustering where I'm not able to give a lot of details. I'm not giving a lot of details around this clustering, but the easiest way to intuitively understand this idea is if my original metric was close to a tree or a hierarchically separated tree, HST, is what it is called, then that we already have that clustering. Okay, but in general, with all these parameters as log, we can find a clustering with all these parameters as log. So there was a log square in the upper bound. There's a log to the 4 in the lower bound. That gives us a factor of log to the 6, and that's the approximation. Okay. Now that's the approximation between our surrogate and the cost. So now how do we decide the inventory policy for that surrogate? This is the inventory that we decide for the surrogate. For each cluster, for each subtree, we can define a virtual backlog, which is the diameter of the parent subtree. So if I am out of unit in this subtree, I would go to the parent and I would go to a random unit within the parent subtree. Okay. So I charge myself the full diameter of the parent, and that is my virtual backlog. So diameter of the parent minus h, that becomes the virtual backlog of each node in the tree, and then I can write the following LP. So for all clusters, when I say cluster, I'm interchangeably using subtree. So for each node of the subtree, I want the total inventory in that subtree to be lower bounded by the scarf inventory, assuming that subtree is a single location with a virtual backlog of diameter of the parent subtree. Okay? Where where this BC is diameter of the parent cluster minus H. Okay. So this is a very, very intuitive policy that you are basically risk pooling across this in this hierarchical clustered way, okay, imposing the inventory given by the scarf solution for a single location as lower bound with the virtual backlog. Okay. So in particular, here the key idea that we are using that was, I think, very clear in the uniform metric was the idea of virtual backlog. You don't pay shipping cost. You don't pay the backlog penalty directly, which you would have done in the independent news vendor solution, but rather you pay that in stages. In this case, in hierarchical way, split across levels. At each level, you're paying the diameter of the parent. And because they were increasing geometrically, that sum of the diameters won't be too large than the largest diameter as well. Okay. What we can show then is that uh, with this hierarchical clustering, choosing my inventory solution with the following LP and using a hierarchical greedy to fulfill, we get a polylog approximation. Okay. Now I want to go back to what I started with. This seems this may seem okay. We are picking the inventory solution um, in a very interpretable way, but this hierarchical clustering and then fulfillment policy, which depends on that clustering, might be too complex in practice. And to that, I'll mention that Amazon last year actually changed their fulfillment network to a regionalized fulfillment network, where earlier if you it earlier the fulfillment was when an order is made, typically the closest warehouse, it is fulfilled from the warehouse that the closest warehouse that has that unit. Okay. And this is very different from what they are actually implementing right now. They split US into 9 regions, and they try to fulfill from the local warehouse, and then if not, then they fulfill from a warehouse within the region, and if not, then they fulfill from a national warehouse. So which if you're in the boundary of the region, it could be a very different solution than than going to the closest warehouse. Okay, for instance, that northwest region, it's a big region. The boundaries are, you might be closer to a warehouse in southwest, but you go to a regional warehouse in northwest. So this has components of this hierarchical clustered solution where you're not going to the closest, you are basically going to a random warehouse in your parent subtree if you are out of stock. Okay, so here this regional structure, these 9 regional structure is creating these 9 subtrees. Yeah, where warehouses in each region are leave. If not, you go to a warehouse within the parent. And this was implemented last year in Amazon. This is actually published. This is available publicly. So much so that it actually made a significant impact on outbound costs and also inventory costs, because when you know how you are fulfilling, you can plan for inventory better. And that is what we saw even in the theory result, because I fixed a fulfillment policy, and there was no need to fix a fulfillment policy upfront. We just needed to plan inventory, and we could adapt to the sequence of or the samples of demand seeing. But because we fix our fulfillment policy, we can plan for inventory better, meaning we can see which regions or what's the nested layers of risk pooling that we want to impose. And it did make a significant impact on fulfillment and inventory cost in Amazon, so much so that it found a mention in Andy Jesse's quarterly earnings call, so which is publicly available. So there are some parallels between the way I should disclaimer. It wasn't inspired by our work, but it was reassuring both ways, because they also know about our work, and it was reassuring that way that there are some similarities between the theoretical approach and what something that is actually implemented. Um, we test our policy, the empirical performance of our policy as well. And here I just want to point out that we to compute the distributionally robust solution, even in the batch fulfillment model where we see all of demand at once. We don't know how to compute it exactly, but Govind Rajan et al. Gave a STP to compute a lower bound for the batch fulfillment, and we saw that our policy was the relative difference was no larger than 6% across various settings that we considered. And in the sequential fulfillment, the gap becomes higher. It goes up to 20%, but still much better than the polylog upper bound that we have. And again, I would point out that there is a log hardness that is sitting here for the worst case bound, but polylog is something that, yeah, we haven't spent enough effort in optimizing the bound. And again, the bound was one of the focus, but really the focus of this work was to get a simple, interpretable policy, both inventory and a fulfillment policy with some theoretical grounding, which this performance bound gives us. Okay, so I'll stop here. I don't know. Yeah, I think I am right on time. But happy to take any questions that you might have.